Hi everyone, this is Tom Yang. Welcome to Method All. Today we'll be continuing talking about stars and bars. But today we're going to cover a tiny little aspect that is on top of last video's stars and bars. Because today we'll be talking about the case where some boxes may remain empty. Okay. Last time we didn't talk about the case where the box could remain empty. Last time the requirement was each box must receive at least one item. This time the boxes can remain empty. Okay? So if you see those types of question on the AMC exams, what should you do? How should you tackle these questions? Well, we're going to talk about this today. And I hope you are going to understand the logic behind this through an example that I'll illustrate. So, I am going to show you the example. So the example is asking for the number of ways to arrange 4 stars to distribute 4 stars into 3 boxes, where some boxes may remain empty. How should you do this? Well, before we begin, let's solve this question through the formula. N equals to the number of identical items, which is 4, and K, I'll use a different color actually, and K equals to the number of distinguishable boxes. So according to the formula, it's 4 plus 3 minus 1 choose K, which equals to what? Which is equals to 3 minus 1. And this is 6 choose 2, which is 15. Okay, so this is the answer we got from the formula. Well, let's prove this using an example. Let's use this example to prove this theorem. Let's draw the 4 stars first. And because this is a stars and bars problem, we're going to use stars and bars. We already used stars. Now we're going to use the bars. And we are trying to distribute the 4 stars into 3 boxes. So in other words, we can phrase it as distributing the 4 stars to separate the 4 stars into 3 groups. So in the last video we talked about this, and you are going to use 2 bars to separate stars into three groups. You use 2 bars to separate the stars into 3 groups. But this time, here is a little variation. There's a variation this time, which is that you can actually place the bars outside of the gaps between 2 adjacent stars. Why? Well, it is because this time we allow empty boxes. And if you place the bars outside of the gaps, you're actually creating empty boxes. You're actually proving the cases in which there are empty boxes. So for example, let's name this as case number 1. This and this are actually the 2 empty boxes that you just created. So case number 1, we create a case in which there are empty boxes. However, you don't always have to have empty boxes. The requirement, the condition says may remain, so which means it's not 100% required. So you could also do something like this. Let's draw the 4 stars again. You can place the bars like this. And in this case, you don't have any empty boxes, right? And that's perfectly fine. Or you can do something like this. Right? And in this case, you don't have any empty boxes either. That's perfectly fine. You don't always have to have boxes that remain empty. It's just it just gives you more freedom to arrange arrange the stars and bars. Well, if you remember from our last video of stars and bars, you probably know that the logic behind this example is to find the number of ways to stick the number of bars into the number of gaps in the stars and bars chart. Well, this time where the logic is slightly different. What we're trying to find is the number of variations. So how many different cases are there in total to arrange the stars and bars as an entirety? What does that mean? What do I mean by that? Well, I'll talk about it now. So let's look at case number 1, okay? There are 4 stars and 2 bars. Well, how many elements are there in total? There are 6 elements in total. There are 4 stars and 2 bars. 4 plus 2 is 6. So there are 6 elements, and this time we'll try to create 6 spots. And we can instead turn this problem into how many ways are there to arrange the 4 stars in the 6 spots, or how many ways are there to arrange the 2 bars in the 6 spots. They give if you learn a little bit of combinatorics, you will know that these two values are the same, because one is 6 choose 4, which is the number of ways to arrange the 4 stars, and 6 choose 2, which is the number of ways to arrange the 2 bars. These two are mathematically different, mathematically the same. And as I already said, this is valid. This is completely valid because you are allowed to have bars outside of the gaps, because we can have empty boxes. And so I can have the star here, and then bar here, and star here. Let's interpret this. What does this mean? This will be group number 1. This will be group number 2. And this will be group number 3. Okay? So group number 1 has 2 stars. Group number 2 has no stars, the empty case. And group number 3 also has 2 stars. And in total, there are 6 choose 4 or 6 choose 2 number of variations. So you can arrange the stars and the bars in 15 different ways. And that is how many ways are there to distribute 4 stars into 3 boxes, 3 distinguishable boxes, where each box must receive, where some boxes may remain empty. That is the same logic that corresponds to the original question or the original example. By calculating how many ways are there to arrange the number of stars and the number of bars together, we solve the question. We turn this question into this example in order to calculate how many number of ways of arrangements are there. And this corresponds to the formula, 15, right? 6 choose 4, or I guess 6 choose 2 is, well, the same as what we got here, which is 15, right? So that's the formula and the example that I just explained, and they correspond to each other, both mathematically and logically. So yeah, this is another aspect of stars and bars. It is common on many AMC exams. There are a lot of questions that I've met that have this topic, and I hope that you enjoy this video, and I'll see you next time.